So we have with us today Lihua Lei of postdoc at Stanford, working with Emmanuel Candès. So I'll hand it over to Lihua. Can you share your screen?
Yeah.
Great.
Okay. So great. So thanks, Brian, for introduction, and thanks, Betsy, for invitation. It's my great pleasure to share my recent work on conformal inference of counterfactuals and individual treatment effects. This is a joint work with my postdoc advisor, Emmanuel Candès. So let me start it by the definition of individual treatment effect that we are using. So in particular, throughout this talk, I will stick with the potential outcome framework. Although later on, if time permits, I will show you that this method also works for some of the causal diagrams and some of the invariant prediction framework. So here, in our setting, we will use T to denote a binary treatment and Y1, Y0 to denote a set of potential outcomes, and X to denote the set of covariates. And throughout the talk, I will take the following three standard assumptions. The first one is RID sampling, or the superpopulation assumption. And the second is suitable. And the third one is strong ignorability, or unconfoundedness. So these three assumptions are pretty standard in the literature, although I would say that this strong ignorability is arguably too strong. And it turns out that we can relax this assumption by doing something like sensitivity analysis, but I won't touch upon this point in this talk. So our goal here is a little bit non-standard. So usually when you say, when you work on a causal inference problem, you have an estimate. And the primary goal is to get a consistent or unbiased estimator of the estimate. And then the secondary goal is to make inference by constructing confidence intervals or some other uncertainty quantification. But here, our primary goal is uncertainty quantification, in the sense that we want to find an interval estimate, C hat, as a function of X, such that it covers the individual treatment effect with a given coverage guarantee, say 90%, where this ITE is defined as Y1 minus Y0. So here you see that this ITE is in principle a random variable, because Y1 and Y0 are both random. So in other words, we want to use a... Hi, Daniel.
Hi, sorry to interrupt. I just wanted to know, in your probability statement there, is X a random variable, or are you conditioning on X?
That's a great question.
Sorry.
X is a random variable. So in other words, this is a marginal coverage in the sense that you can view this as the expectation of conditional coverage where it is conditioning on X. And we want this quantity to be at least 90%. Yeah, that's a great question. Later on, I will spend a lot of time on this, but yeah, you'll see. Okay, so once we have this goal, then we can see that at least we can have two types of tasks. The first one is for subjects in the study, where only one of her potential outcome is missing. Then later on, I will show you that it's reduced to counterfactual inference in the sense that we only need to make inference, or we only need to find interval estimate that cover her missing potential outcomes with the right coverage. Well, for subject not in the study, both of her potential outcomes are missing. So in this case, we must make inference on both potential outcomes. And that's what we call pure ITE inference. And you will see that there's some fundamental difference between these two, in the sense that, roughly speaking, the counterfactual is identifiable in some sense, not in the usual sense, but the ITE is not. So because there's always a hidden correlation structure between Y1 and Y0. But later you will see that that's why we stick with interval estimate, because we know that if we want to get a consistent point estimate for a non-identifiable parameter, that's impossible. But if you want to get an interval estimate, it's possible. So there's some fundamental difference between point and interval estimate. But later on, I will expand on that.
So the last expression in that box thing was y1 and y0. That y is just some new random individual. Is that right?
Yes, exactly. Yeah.
Okay.
Yeah. So here is, so C hat is obtained from our observed data. And this new X and ITE correspond to a new observation. Yeah. So another interpretation is that now given, so C hat is trained on our data. And then suppose you have future population with infinite sample size. Let's say the future population is X1, X2, or to X infinity. Then on average, so their average coverage will be at least 90%. That's another interpretation. But
so are you going to have to say something about the distribution of X's in this other population? Or
that should be the same as your observed data. Yeah.
Okay, so you're saying the future population has the same distribution of X's as what you see in your data set.
That's right. Yeah. Yeah.
Which is not really that reasonable, right?
We can generalize to the case where the future population has a covariance shift compared to your observed data, but the y given X part should be the same. Okay. So that's the usual story about generalization. So if X changes, then you can still handle it. But if y1 and y0 given X changes, that will be much more challenging. But we can handle the first case. Later on, I will have one slide showing this.
It's all just going to lean super heavily on the IID assumption, right?
That's right. Yeah.
That's where the same X distribution comes from, Dan. It's that you're pulling a new IID observation from the exact same IID distribution.
Yeah.
Thanks.
Great. So, okay, before that, and because this is a causal reading group, so I intentionally put this provocative slides in the front so that it can inspire some discussion. So the first thing I want to say is about the contrast with Kate, because the literature on individualized treatment effect is quite rich over the past few years. And mostly, I think people focus on this estimate, which is the conditional average treatment, Kate. So this estimate is defined as the conditional expectation of ITE given X. So the first thing I want to highlight is that the Kate is not necessarily equal to ITE, with only one exception, that ITE is a deterministic function of X. And here I wouldn't say Kate is bad. I think Kate is very good. Among all this individualized estimates, I think Kate is a very reasonable one. But here I just want to highlight several limitations of Kate. So the first one is Kate, by definition, ignores the uncertainty of the response around the Kate function. In the sense that we know that IT is in principle a random variable. And here Kate is taking expectation. Although it's a conditional expectation, but it's still an expectation. So unless you believe that your covariant information is fine enough to explain away most of the variation in ITE, Kate is still a group average treatment effect. So here, this is a simple illustration. Is that suppose your covariant information is not that fine, and then you could still have 3 different scenarios with the same Kate. Well, in the first scenario, everybody get a positive ITE. Well, in the last scenario, only 20% of them get a large positive ITE, while all the remaining ones get a negative ones. So if you are using Kate, you cannot distinguish these 3 cases. But in the first case, you should definitely recommend this treatment. Well, in the third case, probably you shouldn't. So the problem is whether we can get a set of covariate that almost fully explain away the variation of IT. I think in practice, it's hard, because if that's the case, we would observe a R² as high as 0.999. If that's the case, I think it's fine. But usually, if we get a R² as 70%, we'll be very happy. That means there are still 30% of variation that is not explained away. So in this case, I think this uncertainty may matter in some cases. And the second one is, now someone may say, in the big data era, we could have a lot of covariates. So maybe that's fine. But then there's another level of uncertainty, which is extremely challenging in this scenario, which is the uncertainty of the K estimator due to finite samples. So there's an impossibility result by Rina Barber this year, which is not on the causal problem, but simply on estimating the conditional expectation of y given x, where y is binary. So she shows that without further assumption on this response curve, you can never get finite sample valid, or you can never get a non-trivial finite sample valid confidence interval for the conditional expectation, even in the marginal sense. So you may say this is a pure theory. And in practice, we always have some assumptions like smoothness, or maybe some finite VC dimension, or things like that. But let's see how things goes. So here, this is a simple simulation results, which I will touch upon later in more details. But here, this is a simulation with 1,000 samples. Well, in the left panel, we have 10 covariates, while in the right panel, we have 100 covariates. And I promise you that everything I simulate here is a smooth function of the covariates, and it's very simple. But then I apply three very popular methods: causal forest, X-learner, and BART, and trying to see what's their marginal coverage of Kate, because each of them can produce a predictive interval for the outcome for Kate, or confidence interval for Kate. And you see that if we set the target to be 95%, they fail to cover, even in this case. So you see that the point here is that coverage is in some sense orthogonal to accuracy. So all the three methods are very good in terms of the accuracy of Kate. But they all use different methods to quantify the uncertainty. But you see that even in this simple setting, the uncertainty quantification is not very successful. Okay, if there's any question, please feel free to interrupt, because I'm intentionally putting it here to inspire questions.
So you're saying there's that these methods produce very little bias, but when you're looking at uncertainty quantification, they do very poorly. Is that what you're saying?
That's a great point. I'm not sure whether this undercoverage is from bias or variance. So I mean,
because I thought you were saying that Kate estimators work well, but that their uncertainty is very poor.
Yeah.
Can you just restate what you were trying to say?
I think by well, I mean, so you see that whenever we characterize the accuracy of the point estimate, there's no universal well in some sense. It's that you say, so all these people, all these methods are proved to be perform well because they are better than some other methods. So of course, their accuracy is not 100%. And usually they compute the mean square error of this method. And they say, okay, this method is better because it has smaller mean square error than other methods. But this small error, so unless this error is 0, then this small error could make your coverage arbitrarily poor if you don't get your standard error correct. So right. You see that, yeah.
So you're not claiming anything. This could be a bias. I mean, this could be both due to bias and variance here.
That's right. Yeah. Okay. I think usually these people give interpret this figure as bias. So they say in this non-parametric estimation problems, the bias is large, so it's hard to cover. But I think I'm not sure. I think it could also be because of this underestimation of the standard error. But it's hard to peel off these two effects.
Oh, sorry. Are you done, Dan?
No, go ahead, please.
I'm never done, Betsy.
Okay, well, let me have a turn. It seems to me that unless you are, unless you're going to subset for x equals little x and get finite sample coverage using conformal inference for that, you're really comparing apples to oranges here. And like the decision-making role that Kate plays is that you see a patient's X's and then you determine a treatment based on that. And you can't do that with the marginal ITE. So I see how the coverage, I definitely see the advantage of guaranteed finite sample coverage, but it's for, it's just, I don't see how anybody who's interested in Kate would also be able to use the marginal ITE.
Yeah, that's a great question. So my answer is twofold. First, you see that for all these Kate methods, in order to get any theoretical guarantee on the coverage or on the accuracy, you have to assume the model is correctly specified in some sense. And in that case, we can also achieve conditional coverage, as I will show later. So our coverage guarantee is also conditional. Yeah, that's the first part of the answer. The second part is, you see that all these methods claim that they have correct conditional coverage under correct model misspecification. Under a correct model.
Mm-hmm.
And here, this plot, so you see that if a method has correct conditional coverage, then this method must have correct marginal coverage, right? Because the marginal coverage is weaker than conditional coverage. And here, this plot is plotting the marginal coverage. But you see clearly from this figure, you see that if the marginal coverage is violated, then there's no way to get good conditional coverage.
Right, because it's an asymptotic claim.
That's right, yeah. So, so I don't think this is a apple to orange comparison in terms of these two parts. So I agree that it's an apple to orange comparison in terms of whether you cover Kate or ITE. But other than this, in terms of the theoretical guarantee or coverage, I think they're the same level comparison.
Yeah, that I understand. I just wonder about, about using the IT for decision making. But I see your point that you can actually get the conditional ITE if you have a correctly specified model.
Yeah.
Was the sample size in these simulations large or small?
1,000, which is pretty reasonable. Yeah. You see here, there are only 10 covariates.
Yeah. Can I ask what sort of outcome was it? Is it binary or?
It's continuous. It's Gaussian. Everything. So here, roughly speaking, y given x is Gaussian, and y0 equal to 0. So you see that, it's a very simple.
And then does this apply to prediction intervals as well? This is confidence interval, right?
Yeah. So later on, I will also show you prediction intervals. So you see that for causal first and XLearner, there are no predicted intervals because these are two frequentist methods. But for BART, I will also consider another version of BART that cover ITE principle.
Okay.
But again, you will see under coverage. Okay, great. I've achieved my goal to get questions here. So the final point is that Kate depends on the choice of x, while ITE is not. Because ITE is just y1 minus y0, but Kate depends on x. So that means, suppose you and I are working on the same data set, but for some reason I got 2 more extra covariates. Then my Kate can be completely different from yours.
I think that's an advantage, not a disadvantage of Kate. I think Kate is used specifically for that exact property, that it depends on the choice of x. But
yeah, that's definitely debatable. I think I raised this point is just because I got a question before, and I think this is so in some sense IT is more in line with Don Rubin's philosophy that we want to define our estimate before getting any data. So we want to get the science table before getting the data, getting statistics. So that's what Don Rubin said. But yeah, I don't think this is a disadvantage of Kate. I think this is just a fact of Kate. Yeah, great. So finally, here I highlighted one of the tweets from Julia Perot that's advocating distinguishing ITE from Kate. But I think you are all expert in this area, so I don't need to say much about this. Okay, now finally, I can get into our method. So let's first look at the counterfactual inference, because this is a strictly easier problem. So here, let's say, consider a testing control unit. And we know that we can observe her x y0, but we cannot observe her y1. So let's say, suppose we can find a C1 hat that covers y1, given t equal to 0, it's bigger than 90%. Then by contrasting C1 hat and y0, we get an interval for ITE. And we know that this ITE interval will cover ITE with coverage 90%, given that this person is assigned to a control group. And similarly, we can do that for the testing treaty units. And so here our goal reduced to find a C1 hat such that it covers y1 with probability at least 90% given t equal to 0. So let me review this whole process. So here we got a bunch of patients or subjects, and then we toss a coin.
Sorry, I apologize. Can you back one second, a slide?
Yeah.
Apologize. And you're considering the observational study setting, right?
I will consider both randomized experiment and observational study.
Okay, I'll let you go on. Okay, go ahead.
Yeah.
Sorry.
So no worries. So here, once we get a bunch of units, we will first toss a coin for each of them based on their propensity score. And in randomized experiment, we can observe it. Otherwise, we must estimate it. But for now, let's so this is just an illustration of the data generating process. Okay. So then we get a set of treaty units and a set of control units. And then the top row are their observed outcomes. And by SUTFA, for this treaty units, the observed outcome are y1. Well, for this control units, they are y0. But in the bottom row, these are the counterfactual outcomes, which are not observed. So for this ones, they are y0, and for this ones, they are y1. So now the question is, how do you infer y1 of this control unit? And a very naive idea is to use the observed units to infer this pink one, because they are both y1. But there's a problem that for this observed units, their observed data distribution can be decomposed into these two terms, where their x distribution, the covariate distribution, is px given t equals to 1, while their outcome distribution is y1 given x. So you see there's no t here. That's due to strong ignorability. And applying the same reasoning to these pink ones, we see that their conditional distribution is still py1 given x. So these two parts are the same. But their covariate distribution could be different because these people are from the control group. So their covariate distribution is px given t equal to 0. So in other words, there's a distribution mismatch between these two populations. And in particular, there is a covariate shift. So this is an illustration of what's going on here. So in the bottom panels, I give the scatter plot of y1 versus x for the real world observations and for the counterfactual world. And you see that these two scatter plots look very different. But if you condition on any x, then that slice is identical. And the only thing that drives the difference between these two scatter plots are the covariate distribution. And now we can rephrase our goal as using the IID samples from one distribution to construct a interval estimate that cover the outcome with 90% coverage under another distribution, where the other distribution differs from the observed distribution only in terms of the covariate. And using the Bayes formula, you can easily show that this covariate shift is proportional to 1 minus the propensity score divided by the propensity score. Okay, so this is actually very standard because it's essentially estimating ATC here, average treatment effect on controls, but it's very similar to the IPW weight for ATT and ATE. So this comes as no surprise. Okay, that's pretty much about the causal part of this problem. And now let's get into the conformal part. So conformal inference is a magical framework that's proposed by Vladimir Vovk in 1990s, and then developed by himself and his colleagues. And recently, it was developed in the statistics community. And I think statisticians have got a lot of interesting results.
So where was it originally proposed?
It's on this. It's by Vladimir Vovk in 1998.
But what literature? You're saying?
Yeah, that literature is in machine learning, but in particular, it's an extension of something called algorithmic randomness theory.
Oh, interesting.
So yeah, it's something established by Kolmogorov in 1930s. Yeah. So I will not give you the details of a detailed review of this literature, but roughly speaking, what this framework can achieve is that given ID samples from one distribution, it can wrap around any black box algorithm to produce a C hat that covers Y with 90% coverage in finite samples for a future observation with the same distribution. So here, there are two features that should be noted. One is it can wrap around any machine learning algorithm. Even if the machine learning algorithm is arbitrarily poor, that's fine. This algorithm will recalibrate this algorithm to produce an interval estimate that has the right coverage. And second, there's no asymptotics. It's finite sample.
So I'm trying to understand the statement here. So the C hat, right? I'm trying to understand what's random, not random. So I understand inside the probability statement, the Y and the X are both random, and they're drawn from that distribution that you wrote down at the bottom there.
Yeah.
But now this is a hat, right?
C hat is also random. So C hat is a function of xi, yi from I from 1 to n.
So is the overall probability thing a random variable? I'm trying to understand what, maybe I'm not being clear. Is the C hat, so is the whole probability an estimator? Or are you integrating out over the observed data?
I integrate out over the observed data.
Okay.
Yeah. So this is called transduction or transductive learning. And there are some very detailed discussion on induction versus transduction in Vovk's book. But there's also another version of this conformal inference, which is called tolerance limit. And that one can achieve a similar guarantee, but conditioning on the training data. But here, I will stick with this transduction setting.
I see. So what I can do is write this as conditional given the training data, and then integrate out with respect to the distribution of the training data.
Right.
Empirical.
Yeah.
And then I end up with a number, and you're saying that number needs to be bigger than or equal to 90%.
That's right. Yeah.
Okay.
Yeah, that's a great question. So you see that here, this setting is taking randomness over both the training data and the future observation. Well, there's another version called tolerance limit that only takes randomness from the future observation. Yeah.
Got it.
Okay, so but here you see, we cannot directly use this framework because we have a covariance shift. But thanks to these two papers, we can adapt conformal inference to this setting, where instead of having, so again, we have ID samples from one distribution, but then this framework, called the so-called weighted conformal inference, can give you a C hat that covers Y with 90% coverage under another distribution with a covariance shift. And in particular, I will stick with one particular method to make things concrete, which is called weighted split conformalized quantile regression. And now I'm gonna illustrate this method. So this method will start by randomly splitting the data into two folds. And in this case, because we only look at the treated units, so we will take the treated units as our data, and then we split into two folds. And in the training fold, we will use any method you like to fit the 5 and 95 percentile of y1 given x. And this means you can use linear quantile regression, or you can use neural nets, anything you like. You don't need any theoretical guarantee for you to get the right quantile. You just need to quantile estimate. And then you apply this to estimate on the calibration fold. Now you get, again, you get two black curves. And once you get this, you compute something called a sign distance of each point in the calibration set, where the sign distance is defined as the distance between each point to one of these two black curves, which is closer to this point, and multiplied by a +1 if this point is outside this envelope, or a -1 if it is inside. So that's why we call it a sign distance. And then we collect all the sign distances, and we got a histogram. So the plain conformal inference will directly work on this histogram, but we will do one extra step because we have covariance shift. So what we are going to do is to reweight this histogram based on covariance shift. So you see now that there's a complicated formula in this slide, but you don't need to parse it. So the only message in this slide is that this weight, or this reweighting function for each sign distance, is proportional to the covariance shift. And so that means if you are in a randomized experiment and you know the propensity score, then this covariance shift is null because it's proportional to 1 minus e divided by e. So in other words, this is a function that's computable, or at least estimable. And then once you get this, you reweight this histogram, and then you take the 90th percentile of this blue histogram, and let's call it qx. And finally, this method will output an interval as these two black curves plus and minus qx. So you see, that's why I call this qx a calibration term, because these two black curves are estimates of the quantile. So if they are correct, that means if we do get the 5 and 95 percentile, then there's no need to calibrate it, because that automatically give you 90% coverage and even conditional coverage. But the problem is we can never trust any machine learning algorithm to give you a correct answer. So because there's always a risk of model misspecification. So in that case, the purpose of this calibration term is to save that misspecification errors so that it can give you at least the marginal coverage guarantee. So that's why I call it a calibration term.
What's happening to the uncertainty in estimating the weighting function?
Yeah, I will get to that.
Okay.
But
This is just magic. Woo.
But let me get into the case where the propensity score is null, so that you don't need to estimate it. And I'll show you how strong the guarantee is. So in this case, we just plug in the true propensity score. And then what we can get is, first, we get a lower bound, showing that the probability this coverage is above 90%. And this lower bound doesn't require any extra assumption. What's magical is that it doesn't even require overlap. And why is that? That's because if we go back, you see that if there's no overlap, then this weight will be infinite. And in this case, you see that there's a math on infinity. So if there's no overlap for that particular x, you will get an infinite predictive interval for ITE. So in other words, this method is in some sense adaptive to the lack of overlap, which is something people really want to see. So in this case, we know that this lower bound, this coverage, doesn't require any assumption other than the IID sampling, SUTVA, and strong ignorability.
Sorry, can I just ask you about this? So
yeah,
it's just outputting, I can't tell you anything interesting if there is no overlap, right?
Yeah,
so
that's right.
I mean, there is nothing to say if there is no overlap. So I don't, like, imagine I didn't do that. Imagine there was no infinity math, as you say, and I just, like, whenever I detected lack of overlap, I just threw up my hands and, like, terminated the algorithm. In what sense is that different from what you're just saying here?
It's no different. Yeah, I'm just saying that because a lot of methods are using. So for example, if the method is doing some extrapolation, so let's say suppose the method is purely outcome based, then I mean, if the model is correct, then you don't need overlap, right? So because you extrapolate from the other part of the covariance space to this part. So in that case, you wouldn't get a infinitely wide confidence interval. So you may think that here the overlap is not an issue. But the problem is we want to say that if the model is misspecified, we should be able to tell you this. But of course, you can do it in a two-stage way, where you first give a threshold for the propensity score. And then you say, we're not going to make any claim for the region without overlap. But for the other part, we make some inferential claim. But so don't take this too seriously. I think that's why I just put it in the parenthesis. So it's just a sanity check showing you that if there's no overlap, then our method is not going to mess up. It will honestly tell you that there's no overlap. Yeah, because a lot of people question why we don't need overlap condition for the coverage. And this is just an answer to that question.
Okay, great. Thank you.
And of course, because this is coverage, so you can always achieve 100% coverage by setting C1 hat to be infinite for every x. So that's definitely not what we want to do. So meanwhile, we want to get a upper bound for the coverage. So we don't want the method to be too conservative. And turns out that we can get a upper bound as a 90% plus a universal constant. Sorry, it's not a universal constant. It's a constant times n to the minus half, where this upper bound holds under two assumptions. The first one is if the outcome is continuous, then the sign distance will be continuous. And then the second assumption is an overlap condition. But
sorry, what are the VIs? I apologize.
Sorry, is that VI is the sign distance. It's,
okay.
Yeah, it's y minus the quanta. Yeah.
Okay, sorry.
So we just need this VIs to be almost surely distinct. So this is a regularity condition, but at the same time, we need a overlap condition. So this is now in this case, we do need overlap, but we don't need the usual strict overlap condition, but rather we only need a weaker one that controls the inverse second moment of the propensity score. And here the constant only depends on this inverse moment. So in other words, this theorem holds for any conditional distribution of y1 given x, because nothing here depends on this. And it holds for any sample size. And finally, it holds for any procedure to feed conditional quantiles, because even in the upper bound, the C doesn't depend on how you feed the conditional quantiles. And so in other words, here, if we give a estimated quantile and the true propensity score, our procedure will give you a trusted or a trustable interval estimate for the counterfactual. But of course, we're not always in this randomized experiments with perfect compliance case. So in general observational studies or in randomized experiments with compliance, we have to estimate the propensity score. And here, I will just state an informal theorem of our guarantee. If you're interested, I will get you the formal one in the end. So let E hat be an estimate of E. So what we can achieve is that, roughly speaking, we can achieve approximately 90% coverage if either E hat is correctly estimated or the conditional quantiles are correctly estimated approximately. And moreover, if the conditional quantiles can be estimated well, then we can also achieve conditional coverage with high probability. So this is the usual conditional coverage guarantee in the literature. And you see that essentially we need a correct model for y given x. And if that's the case, we can also be adaptive to that to achieve a stronger guarantee. So you see that this is very similar to the double robustness for ATE, because we only need one of the model to be correct. But I want to highlight that this double robustness it's actually fundamentally different from the double robustness for ATE. Because for ATE, we say, so double robustness is actually a phrase that is, I would say, abused in causal inference literature, because people are using this word in different contexts with different meanings. And for the ATE, this double robustness means that if either the propensity score model or the outcome model is correctly specified, then you get a consistent estimate of ATE. So you see that there, the double robustness is in terms of consistency of a point estimate of a marginal parameter, ATE. But in our setting, our double robustness, it's the same as that in terms of the conditions. But the property that we achieve is the correct coverage of an interval estimate, where this interval is individualized. So this is, so although we say this is a double robustness, but it's really an apple to orange comparison if we want to compare this double robustness to the classical double robustness.
So can I ask a couple questions here? So so I'm just trying to understand, let's say I had 10 observations, okay? And I use machine learning to estimate E hat, and I use machine learning to estimate Q hat.
Yeah.
What does this statement mean about, so what is this, the statement at the bottom of your informal theorem say?
Yeah,
it doesn't, go ahead.
Sorry, yeah, in that case, it doesn't give you anything. So you see that in order for this theorem to hold, you do need a approximation here. So if you only have 10 observations, there's no way to estimate the propensity score well, or the control quantile.
Right, so I'm just trying to understand what these little the slash sims mean, whatever these slash approx means in LaTeX terms. So what does it mean that E hat is approximately E of X? And how does that have to do with sample size and the machine learning? Or you don't have to, if you're going to come to it, then we can do it later.
This is a backup slide. It's just for this particular question.
I want to know about this too.
Yeah. Okay. So maybe let me spend some time parsing this. So you see, first, this is in our paper. This is an asymptotic argument. Although if you look into our proof, you can turn this asymptotic proof into a non-symptotic convergence rate analysis. But we haven't done that yet. But we will do that because one of our reviewer requests this. So you will see some refined result in our new version. But you see that for asymptotically, first, you do need this E hat to be consistently estimated. So that's what we mean by approximate equal. So that little tutor means. So the first assumption that E hat approximately equal to E means this.
Okay, so I gave you a sample size of 10, and I've done an estimate, and let's suppose I have an estimator, a machine learning estimator of E hat.
Yep.
And let's just say that's consistent.
No, but there's no way to get a consistent estimate with 10 samples.
No, I'm just saying, obviously as n goes to infinity, right?
Yeah.
We'll have the result, but now I have finite samples, and my finite sample size is 10.
Yeah, so in that case.
So I'm trying to understand, how do I apply your theorem in the context of final? What is it? What is the application of your theorem to finite samples, and what can I say in finite samples about your 90%?
Yeah, so here you see that in order to do that level of finite sample analysis, so first, for observational study, our guarantee is not finite sample, it's asymptotic. Okay. Yeah, but you can turn it into a somewhat non-asymptotic version, which is instead of putting a small o1 here, you put a, say, n to the minus something, say n to the minus half here. And then once you have a convergence rate here, and you have a convergence rate in the outcome equation, then you can turn this coverage, you can turn this small o1 in the coverage guarantee based on those convergence rate. So for example, if you have n to the minus third rate for propensity score, and then n to the minus quarter rate for the outcome equation, then you will have some n to the minus something for the coverage. Yeah, so we can definitely make that analysis refined to give you this particular exponent. But you see that we didn't do that because essentially that doesn't say much more than this asymptotic result. Because In order to use it, you still require n to go to infinity.
So what advantage does this have over classical confidence intervals in the case where it only holds asymptotically? Or I guess maybe I should say classic prediction intervals.
Yeah. So let me get back to this. So if the advantage is that, so first, there are two advantages. So the first advantage is this double robustness, which I don't think it holds for any other predictive intervals.
It does if you use the right variance analysis. Like if you take a classic double robust model and you do the variance analysis correctly, you'll get a correct asymptotic variance estimator if one model is incorrect.
So I thought that was an open problem with what Marco was talking about. And I'm forgetting. Am I getting that right?
That's right. That's an open problem. So it's that for ATE, so ATE is a marginal parameter. It's a function of the underlying distribution. In that case, yes, you can do doubly robust inference. So
but not prediction. Okay,
right,
got
not
it.
prediction. Yeah.
Got it. So it's getting you valid confidence intervals for a different parameter, specifically the prediction.
That's right. Yeah.
Okay.
Yeah. So this is the first advantage. And the second advantage would be, like a lot of procedures are asymptotically equivalent or given asymptotically equivalent conclusions. But in practice, although they're asymptotically equivalent, there could be one method that outperform the others. And I think this is somewhat the key. So for example, we know that permutation test performs well, but it's asymptotically equivalent with many other tests. But I think that the main reason that the permutation tests tend to be robust in finite samples is because that there exists some scenarios where the permutation test is valid in finite samples. And here, applying the same reasoning here, our method, at least for a randomized experiment, can achieve the guarantee in finite samples. So it somewhat give you a more robust certificate beyond the asymptotic guarantee. Yeah.
It's relying on asymptotics for different things.
That's right. That's right.
Yeah.
Yeah.
Thanks.
Great questions. So one final comment on this, on the counterfactual inference part, is that previously we considered a particular covariance shift where this blue distribution is the distribution of x given t equal to 0. But in general, it's not hard to generalize this whole thing to arbitrary covariance shift. So for example, if you want to get a ATE type inferential guarantee, then you simply set the weight function to be the inverse propensity weight. And if you want to get ATT, meaning that meaning that there's no covariance shift, then you don't need to even do weighted conformal inference. You can just do the standard conformal inference. And finally, if you have a different population with a different covariance distribution, and suppose you can estimate the covariance shift between your study population and the other population, then you can also do this generalization. So this is something important because like in the literature on generalization, we more or less need to know what's the density ratio between two populations. But here, if we know that, then we can also do that. Okay, so that's pretty much about counterfactual inference. And for the sake of time, I will quickly go through this IT inference part. And first of all, I want to emphasize that there's a very simple way to get valid intervals for ITE by just applying Bonferroni correction. So you see that the counterfactual inference can give you valid confidence predictive intervals for y1 and y0 separately. And so if we want to get 90% predictive interval for ITE, then what we need to do is to get a 95% interval for y1 and 95% interval for y0, and then contrasting them. So by contrasting, I mean you take the upper end minus the lower end as the upper end. And then you take the lower end of C1 minus the upper end of the C0 as the lower end. So you can easily show that if each of them has 95% guarantee, then this one will have 90% guarantee, regardless of the correlation structure between Y1 and Y0. So this is something special about interval estimates, because here we know that the distribution of Y1 minus Y0, or ITE, can never be identified because Y1 can correlate it with Y0 arbitrarily, but you can never detect it. Maybe you can partially identify some of it, but you can never point identify it. So in terms of point estimation, it's hopeless. But for interval estimate, it is possible, and it's very simple. And one reviewer asked us, what's the relation between this and Frechet-Hopding bound? And turns out, if you know this Frechet-Hopding bound, it's essentially a union bound. And here we are using the same argument because Bonferroni is the union bound. And in our paper, we also introduced two other methods. Roughly speaking, we use the counterfactual inference to generate ITE intervals for subject in the study. So we do some data splitting. And then we treat a part of our data as subjects in the study. And then we first construct ITE intervals for those units. And then we try to generalize these intervals to subjects not in the study. And again, we can propose an exact version, meaning that this version has exact guarantee by using a secondary conformal inference. So again, for randomized experiment, it's valid in finite samples. And for observational study, you have that doubly robust guarantee. But we also propose an inexact version with no theoretical guarantee, but somehow we find it work well in many settings, but we cannot demystify it. So, but the bottom line is we propose 3 versions of this for ITE inference, where 2 versions are exact and the other one is not. And for the sake of time, I think I will skip this part and I will go straight into the simulation results because I think there's something really interesting about simulations.
Do you have just an empirical example? Did you say you have an empirical example where you can just show us like what your procedure will output?
Yeah, this is what I'm going to show you.
Okay.
So the first one is a pure simulation, but the second one is a simulation based on a real data. So this one is the one I show you at the beginning. And this is a variant of the example from the Causal forest paper. In particular, we further simplify that. And our goal is to give you a very simple data generation process to show that even on the simple DGP, things can go wrong. So here we simulate X as Gaussian with independent or correlated entries. And the dimension is either 10 or 100. And we also set Y0 to be equal to 0. And this means the ITE inference is reduced to counterfactual inference. And we simulate Y1 given X as a Gaussian variable with a smooth mean and a smooth variance. And the variance could be homoscedastic or heteroscedastic. But even in the heteroscedastic case, the variance is a smooth function. And finally, this example has very good overlap. And also the propensity score depends on only one coordinate in a smooth way. So before showing you the results, I only say that we have R package, and you can download it from my GitHub. And here, this R package can implement everything I'm talking about in this talk, and also implement something that I haven't been talking about in our paper. So you can play with it if you are interested. And so the first figure I'm going to show you, it's a sanity check. It's the apples to orange comparison. And this plot is to show you the marginal coverage of Kate. So you see that this is an apple to orange comparison because our method is not designed to cover Kate, while the other methods are designed to cover Kate. So this method is real. So this plot is really a sanity check. So you see that the first 3 methods are our methods, but because our method can wrap around any algorithm to estimate conditional quantiles, so we try 3 methods. The first one is to wrap around BART. And the second is quantile boosting. And the third one is quantile random forest. And so you see that first, sorry, by the way, I should say each column gives you a setting where this means homoscedastic, this means heteroscedastic, and this means you have independent covariate, and this means you have correlated covariate. So you see that for the bottom three methods, although they are designed to cover Kate, but there exist cases where the coverage is not good. And for our method, you see that our method has 100% coverage almost. That means our method is conservative in this case. So that's not hard to imagine, because in this simple case, covering ITE should be much harder than covering Kate, because ITE is random, but Kate is the point. It's a number. So that means our method could be very conservative if you want to use it to cover Kate. But as a reassurance that in statistics, being conservative is usually slightly better than being anti-conservative, although we want to be right on the middle. But if we cannot, then usually we want to go a little bit more conservative. So this is a sanity check, and there's no more to say. And the second plot is the real thing we want to compare with. It's the marginal coverage of ITE. And you see that the causal forest and X-learner, they're not designed to cover ITE. So here, although they have poor coverage, but it's not surprising. And I wouldn't take this as a disadvantage of these two methods, because they're not designed to do this. But for BART, we know that if we replace the credible interval with the predictive interval, then we can get a version of BART that in principle should cover ITE. And here, we actually use that version of BART. So you see that for homoscedastic case, BART has an almost perfect coverage. And that's not surprising, because BART assumed this homoscedasticity. And also BART is very flexible in terms of estimating this type of smooth response curve. So you see that in this case, BART is good. But if the errors are heteroscedastic, BART can undercover. You see that here our goal is 95%, but BART can achieve only 80% of coverage. That's pretty poor. But our method, regardless of which method to wrap around, always have 95% coverage. And by the way, in this case, the propensity score is also estimated. We're not using the correct, the true propensity score. So you see that this is in line with our theorem, showing that our coverage is very close to our target level. It's not above, it's not below. It's right on that. And whenever we talk about coverage, we should always talk about length, because coverage versus length is like type 1 error versus type 2 error. So here, in each plot here, I give a blue line, which is the oracle length. And this oracle length is simply to assume that we know the whole data generating process. And then the oracle interval would be just the 5th and the 95th percentile of, the 2.5 and 97.5 percentile of y given x. So this interval is the oracle interval, so no interval can beat this. So then once you know this, you can calculate the average length of this oracle interval. So in some sense, this is the length that you can never beat. And you see that for homoscedastic case, BART has achieved this near oracle length. Well, for the heteroscedastic case, they're even shorter than that, but that's not because it's better. It's just because they're undercover. And for our method, you see that for homoscedastic case where BART performs well, if we wrap around BART, we also get this near oracle length, meaning that we're not losing much, even with 1,000 samples. But in these heteroscedastic cases, when BART doesn't perform well, you see that the length of our methods become much worse. And in some sense, I would interpret this as a good thing, because somehow our method detects that BART is not doing a good job in this case. And so the calibration term will has a high variability, making the intervals unstable. But I think this is good because we want to be honest about what we can say with the methods. And this is where the honesty comes from. But you see, if we wrap around boosting and random forest, then things are overall perform well. So they're all above the oracle length, but not by much. But here you see that we only have 1,000 samples. And in particular, we only have 470 treaty units. So here the effective sample size is only 470, but you can still do this. So I think this is pretty promising.
Can I ask one question?
Yeah, sure.
So I have to leave it. Unfortunately, I have to leave it in a couple of minutes, but I just wanted to just make sure I understood the big picture is that if I have a data set with 1,000 people, you're going to give me 1,000 intervals for each person. What is your procedure outputting for each person?
It will output a function as a C hat X. So that means once you have a new observation.
Because I have a new observation with an X.
Yeah.
Okay, and it's going to output me for that given X an interval.
Yeah, that's right. Yeah.
And so if I give you 1,000, new people with different X's, I'll get 1,000 intervals.
That's right. Yeah.
Okay.
And the guarantee is that over that 1,000 people, new people, the average coverage would be about 90%.
Lihua,
So
we do have to close the meeting.
If I'm going to use this, go ahead.
Sorry, we just have to close the meeting pretty soon. So if Lihua has any more slides, maybe you could go through them quickly, and then.
Yeah. I can wrap up soon.
I'll contact you offline. I have some more questions. So, but this is really amazing. So love it.
Thank you, Daniel.
Bye-bye.
Bye-bye. Yeah, so I will wrap up in 2 minutes. Is that okay, Brian? Okay.
That's fine.
Yeah.
Thanks.
So the final plot is about conditional coverage. And the message here is that you see that our method, although we only give the marginal coverage guarantee, but at least in this data set, the conditional coverage is good. And in particular, we see that the CQR BART is wrapping around BART, but where BART has poor conditional coverage, well, CQR BART can have better one. Okay, so I will skip the second simulation, which basically says the same thing as that one. And finally, I will wrap up. So in this talk, we propose the conformal inference of counterfactuals and individual treatment effects, which is reliable in the sense that for randomized experiments where the propensity score is known, we can achieve near exact coverage in finite samples with any black box algorithms. While for observational studies, it can achieve a doubly robust guarantee of coverage. And finally, if you are interested in this conformal inference, you can check out the tutorial on conformal inference by my postdoc advisor, Emmanuel Candès, at this Bernoulli IMS One Word Symposium. I think you can simply search this and you will find a video on YouTube, which is an excellent tutorial on conformal inference with title Conformal Inference in 2020. And with that, I would like to thank you all for your attention and great questions.
Thank you very much. Does anyone else have questions for our speaker?
Thanks so much, Lihua.
Thank you, Betsy.
I understand this better each time I hear it.
Thanks.
Yeah, I just want to say this is fantastic work. It's very impressive, very useful. I love your problem formulation. Yeah, what you're targeting is very useful.
Thank you,
and one thing I would propose, if you want to talk later, we could talk offline about applying it to some medical studies to see how informative it is.
Yeah, that would be great. Yeah,
that would be really interesting. But I mean, the theory, the ideas are amazing. It's really very impressive that you did this. So yeah, and great talk. Very, very clearly explained as well. Thank you.
Thank you. Yeah.
Hi.
Oh, sorry. Go ahead.
I'm sorry. This is Yvonne, and actually, I'm a very old member, but rarely coming in here. Lihua, this is wonderful talk. I just wanted to say, learn a lot. I am not into machine learning, but you talk me into it. It's really wonderful. I was wondering how, I wanted to start with the beginning, which is your randomized experiments, how to implement these to get your near exact coverage in the, with any black box. But I will how to say, learn from? Is the first step will be nice to do the tutorial?
Oh yeah, so in terms of the implementation, you can check out our package. So here you see there's a website of my package, and where you can find a tutorial in these articles, and also you can check out the manual of this package. I think it's well documented.
Oh, thank you so much. Very, very helpful. I will learn from there. Thank you.
Thank you. Yeah. Let me know if you have any questions on the package. I would like to help.
Sure, thank you. That's very nice of you.
Anything else? All right, so I think we can wrap it up. Thanks again, Lihua, and thanks everyone for coming today.
Thanks, Brian, for organizing this.
So long, everyone.
Thank you. Appreciate it. Have a good day.